So we'll give it the old college try here. All right, Chemistry 3101. This is Chapter 9, the alkynes chapter. I probably make this joke every time, or tell this story every time I teach this chapter, but years ago there was an ACS, an American Chemical Society conference, and I think the theme of the week was alkynes, and they were handing out bumper stickers that said it takes alkynes to make a world. Anyhow, pretty great stuff. Anyhow, so an alkyne, is when we have a carbon-carbon triple bond like this, but we usually don't write out the carbons explicitly. We usually just say, okay, you've got a triple bond here like this, and it's implied that there is a carbon here and a carbon here, right? You should know that because you can, I'm sure you can all draw a bond line structure by now. So if we have an R group on each end, we call that an internal alkyne. So this would be an internal alkyne. And then if you had like an R group and then you had a hydrogen on one end, then we call that a terminal alkyne. So we call this a terminal alkyne. Why? Because it's the end of the compound, so to speak, right? If it ends with a hydrogen, it can't go any further than that. And then the simplest of all the alkynes is this one right here. So if you have two hydrogens, one on each end, this has got two names. The systematic name would be ethyne, but nobody calls it that. The common name, so the common name of the simplest possible alkene, so common name is acetylene. Acetylene. And acetylene, I'm sure you've heard of it. It's a gas at room temperature, and it's used in welding. And the reason why is because it burns with a flame of it at about 2,800 degrees Celsius, so it's a really hot flame. And of course, if you wanted to draw the bond line structure of acetylene, I mean, this 3 lines means the same as, but all you have to do is write this. So I can't think of an arrow that would be proper here, but it's the same thing as just writing this, right? That's acetylene, just 3 lines like that. That would be the bond line structure of acetylene. Anyhow, so let's get into it here. And alkynes are molecules that possess a carbon-carbon triple bond. And so what's being shown here is an orbital overlap diagram of acetylene. So what they're showing here is the carbon-carbon triple bond, and they're drawing the acetylene molecule. All right, so you know that the first bond between any two atoms is a sigma bond. And so we have sigma, sigma, sigma bond. But you know that any bond after a sigma bond is a pi bond. So we have 2 pi bonds in acetylene. And you see that they come from the overlap of p orbitals, right? Here's one p orbital on one carbon. Here's a p orbital on the neighboring carbon. Okay, and those ones are kind of vertical with the page. And you see the orbital overlap shown here by those dashed lines. But then you have 2 p orbitals that are kind of perpendicular here, the way that they're drawn like this, and they overlap as well. And so those make up the 2 pi bonds. And of course, this is a sigma bond shown here, and the other 2 sigma bonds are shown here and here. Okay, so you have to have a little bit of an idea of that. And you should also know the hybridization of the carbon. In a carbon that possesses a triple bond and a single bond, it is sp hybridized, right? This carbon is sp hybridized. So you should understand the hybridization. And then what about bond angles, right? You should also know the bond angles, right? If we draw our acetylene molecule like this, okay, you should know that the bond angles here and here, they're both 180 degrees, right? So the molecular geometry is linear at both of those carbons. But what the main point of this slide is it's showing the electrostatic potential map of acetylene. And you see that we have a lot of electron density in between the 2 carbons, right? Because we have those 2 pi bonds and the sigma bonds. But we know that pi bonds are weaker than sigma bonds. And so what that does, it enables an alkyne to behave like an alkene. And that means that it can react as a base, an electron donor, or a nucleophile. And we're going to see examples of both of those in this chapter. So many of the addition reactions that you learn in chapter 8, so many of the addition reactions for the alkenes, so that was chapter 8, also work for alkynes. So we're going to see many of the same concepts in chapter 9. So before we get into the nuts and bolts of nomenclature and the kind of reactions you can do with alkynes, let's just talk a little bit about them. So I've already mentioned acetylene, which is this compound. So you could write it like this if you want. That's a partially condensed structure. Again, we just write it like 3 lines like that is the bond line structure. Acetylene is the simplest possible alkyne that we can have. Again, the systematic name would be ethyne, but nobody calls it that. Everybody calls it acetylene. And it's used in blow torches. Blow torches, the reason why I explained earlier is that the flame that it produces burns at about 2,800 degrees Celsius. And it's also used in synthesis. And we are going to do this a lot. We're going to use acetylene in synthesis a lot in chemistry 3101 and chemistry 3111 as well. There are more than 1,000 different alkyne containing natural products that have been isolated, not nearly as many as alkenes. And then one of them is this interesting molecule here. This is histrionicotoxin. So this is the poison that poison dart frogs excrete anyhow, and then they rub the tip of the arrow in the poison and shoot their prey or whatever. Anyhow, I'm not really going to ask you anything about histrionicotoxin, but you can see that it does have 2 alkynes in it. So 2 of those functional groups. Well, I wanted to go over the nomenclature of alkynes. One of the recurring themes that you'll see in organic chemistry is whenever you discuss a new functional group, you kind of always begin by learning how to name that, because you can't really talk about it unless you can give it a name. And so the good news is that if you learn how to name the alkenes and alkanes in chapter 4 and in chapter 8, then you'll be able to name alkynes, because we only make a few minor modifications, okay? So the first thing, like an alkene, when we name an alkyne, we find the parent chain that contains the carbon-carbon triple bond. So it's got to have that carbon-carbon triple bond in it. Got to have the triple bond, okay? Got to have the triple bond. And you want to number it in such a way that you give the triple bond the lowest possible number. Then you identify and name all the substituents: methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl, etc. You give a locant for every substituent. Again, like I previously stated, you give the carbon-carbon triple bond the lowest number possible, just like you did with an alkene. Then you list the numbered substituents before the parent in alphabetical order. You ignore prefixes except iso, cyclo, and neo. And then the carbon-carbon triple bond locant is placed either just before the parent name or just before the -ine suffix, right? And I'll give you an example of that. Let's say you had this compound here, so right, you could call this, so this has a total of 1, 2, 3, 4, 5 carbons. So you could call this 2-pentyne, or you could call it pent-2-ine. Either one is perfectly acceptable. And we saw something similar with alkenes, and in organic chemistry too, you'll see something similar with alcohols and other functional groups as well. So we covered pentane, pentene, and pentyne already. Now this compound, the proper name for this compound would be 1-pentyne, right? Because we number it in such a way that we want to give the carbon-carbon triple bond the lowest possible number, just like this compound would be 1-pentene. Now, if we are finding the longest carbon chain in this compound here, we see that it's 8 carbons, and you might think, well, the longest carbon chain is this one here in this compound, but remember that chain doesn't contain the triple bond, right? You have to include the triple bond, so you would start numbering here, 1, 2, 3, 4, 5, 6, 7, and since we have a propyl group at carbon 3, we would call this 3-propyl 1-heptyne. So 3-propyl 1-heptyne. And if you named it as 3-propyl hept 1-ine, that would be acceptable as well. Again, assign a locant to each substituent, give the carbon-carbon triple bond the lowest possible number. We see the correct way of naming here on the left. You can see that this compound has 3 methyl groups. You've got 3 methyl groups, 2 at carbon 5, 1 at carbon 6. And so you would call this 5,5,6-trimethyl. So let's scribble it down here. This would be 5,5,6-trimethyl 2-heptyne, 2-heptyne. Or you could call it 5,5,6-trimethyl hept-2-ine. Either one, again, is perfectly fine. And you see the name shown over here, okay? So, of course, we list our substituents in alphabetical order, and students are usually very good at that. Now, there are some common names like acetylene that I taught you already. you've got to know acetylene. We're going to use it over and over again. So let me remind you again, acetylene is this compound. We usually just abbreviate it with the bond line structure like this. It is the simplest possible alkyne in the universe. It is C2H2. That's the molecular formula, nothing more than that. However, when we're naming acetylenes, or sorry, alkynes as with common names, we name them as acetylene derivatives. So what you do is if you can identify the alkyl group, you name it, and then you follow up with acetylene. So this would be methylacetylene, diisopropyl acetylene. And here you have two different groups, so you just list them in alphabetical order. So again, for this one, you just go A to Z, right? So phenylpropyl acetylene. And if you're wondering, well, wouldn't this have a systematic name as well? Yes, absolutely, right? The systematic name for this would just be propyne, but you can call it methylacetylene. Either one is fine. I already went over the idea of a terminal alkyne, so that's one that ends off with a hydrogen like this, and then an internal alkyne is one that has two carbons attached to each one of the sp hybridized carbons. And the reason why we actually spend so much time in this chapter talking about terminal alkynes, and we're going to get to this in just a little bit, is that you can take a strong base, so I'll just put here base, and you can deprotonate at the terminal alkyne and make what we call an alkanide. So we call this an alkanide. All right. So an alkanide is the carbanion of a terminal alkyne. Now, if you deprotonate acetylene, okay, so if you treat that with a strong base, you can also make a carbanion. But when it's the carbanion of acetylene, we call that acetylide. Acetylide. So acetylide would be a type of alkanide. But again, if we have an R group on there, we call it an alkanide all the time. All right, and we're going to see those terms come up once in a while in this chapter. So let's try naming a couple of compounds here. It says provide a systematic name. We could do common as well, or common. Okay, so why don't we use black ink for the systematic, and then we use blue ink for the common name. So if I circle this carbon in red, and if I circle this carbon in blue, does anybody have an inkling on which one of those carbons I should start numbering? Because either way, I'm going to have a 3-hexyne. Right? Wouldn't matter which end you start at. You'd end up with a 3-hexyne. It should be the red one, right? Because you go for the tiebreaker, which is the methyl group. Thanks a lot, Hannah. So we're going to start numbering down here. So let's start here. So we've got 1, 2, 3, 4, 5, 6. So we've got a 2-methyl 3-hexyne. So we would call this 2-methyl 3-hexyne. Yeah, but we could also name it as an acetylene derivative. Right here we have an isopropyl group, and here we have an ethyl group. So you could call it ethyl isopropyl acetylene. That would work too. Acetylene. There we go. I was supposed to use blue, wasn't I? Let's switch that up. There we go. All right. So for the next one, of course, we're going to start numbering at the end that is terminal, right? The end that has the hydrogen attached directly to it. So we're going to go 1, 2, 3, 4. So we've got a 3,3-dimethyl 1-butyne. So 3,3-dimethyl 1. Oh, we'll just do it this way. Nope, 1-butyne, like that. And if I wanted to identify the common name, I've got a tert-butyl group over here, so you just call that tert-butyl acetylene. So tert-butyl acetylene. Either one would be acceptable. I don't have a problem with any of those. And even the systematic names, if you wanted to call the first one 2-methyl-hex-3-ine and the second one 3,3-dimethyl-but-1-ine, both of those would be acceptable as well. All right, give me a thumbs up if you're like, I think I could name these. Yeah, awesome, awesome. And of course, you're going to have to practice them a little bit, but usually students are very good at naming alkynes if they mastered the nomenclature of alkenes. Well, I'm going to take you back all the way to chapter 3. So it says recall, and this is recalling something from chapter 3. Okay, that was our acids-base chapter. We talked about terminal alkynes and what their pKa was. We said if you have an alkane, like ethane, alkane, We said the pKa of a carbon-hydrogen bond with a sp3 hybridized carbon, so this is sp3, is around 50. If you have an sp2 hybridized carbon, it's 44, 45. But then for an alkyne, so if you have an sp hybridized carbon-hydrogen bond, that hydrogen has a pKa of 25. So it's a lot more acidic than ethylene and way, way, way more acidic than ethane, acetylene is. So what does that mean? The idea here is that you can deprotonate an acetylene derivative or a terminal alkyne can be deprotonated, okay? And how do we justify or how do we rationalize the difference in the relative acidities here? If we think of AREO, so atom resonance induction orbital, remember that what we're doing here is that we're rationalizing the relative pKa's based off of orbital, right? Remember that we said that the sp orbital is smaller than an sp2, which is larger than an sp3. And since the sp orbital is smaller, the electrons are closer to the nucleus, and therefore they're more stabilized. So again, you know, what's the whole rationale for us discussing why this proton is so much more acidic than the others on here? The reason why is because we can deprotonate an alkyne. So we can deprotonate acetylene to get an acetylide. And just to review, if you take a terminal alkyne, like this, you can also deprotonate it with a base. So I'll put base like this, same thing. And if we do this, we get an alkynide. Okay, so we call this an alkynide. So alkynide and acetylide. You need to know the difference between the two of those. All right. And the next thing that we're going to take a look at well, maybe not immediately, but in a little bit, is that these can be nucleophiles, right? They can be bases as well, right? But they can also behave as nucleophiles. So we're going to see how we can make carbon-carbon bonds using an alkynide or an acetylide. Very useful chemistry. So again, I've already covered this with you. So this is just a review of AREO, right? And it just shows the relative sizes of the sp3, sp2, and sp hybrid orbitals. sp is the smallest, and usually students know this very well at this point. So again, the electrons are very close to the carbon nucleus, so they're more stable, and that's the answer to that. All right, so let's take a look at deprotonating an alkyne. So let's say we take acetylene, and we want to deprotonate it, okay? So we want to remove one of these protons. So what is the base that we're going to use here? Because we have to use a very strong base. And you're wondering, well, maybe sodium hydroxide. That's a really strong base. Well, it turns out that sodium hydroxide is actually not a strong enough base to deprotonate an alkyne. I'll show you why. It's shown down here at the bottom. So just follow along with me. If you were to try to use NaOH, which is a very strong base, to deprotonate a terminal alkyne, and you compare the pKa value of your acid versus your conjugate acid, well, the alkyne is going to be the weaker of the two acids, and so the equilibrium is going to lie to this side. So that means that sodium hydroxide is not effective at deprotonating an alkyne. So what we have to use is a stronger base. We got to bring out the big guns on this one. And the big gun that we use is this base. We have to use a very strong base, which is sodium amide. So NaNH2, this is called sodium amide. Okay, and I know you're probably thinking, hold on. Didn't you teach me that this functional group, like weeks ago, that this is called an amide? Yes, this is the amide functional group, okay? But this is another use of the word amide. This is an amide ion, is NH2 minus. So if you draw the Lewis structure, it looks like this, okay? So when you see NH2 minus, like this, that's an amide ion. So sodium amide is a very strong base, stronger than sodium hydroxide. And if we compare the pKa of the alkyne versus the conjugate acid, which is ammonia, well, ammonia is much more basic, or a much weaker acid than a terminal alkyne. And so therefore, sodium amide is going to work very effectively at deprotonating a terminal alkyne. So again, if we want to deprotonate a terminal alkyne, the base that we're going to reach for most of the time, we'll just put it here, is going to be sodium amide, NaNH2, right? Na is positive, but NH2 is negative, and that's going to be our base, sodium amide. We're going to use that a heck of a lot in this chapter. So again, I covered what an alkynide is, and we've covered that whether it's Acetylene or a terminal alkyne, you're going to want to use sodium amide. So I'll write this in here again. Sodium amide is the best base. Maybe not the best, but it's the one that we use the most. It says others can be used as well, and we might see some others in our journey through this chapter. So just to review, if you want to deprotonate a terminal alkyne, you've got to use a base that has a conjugate acid that has a pKa higher than the terminal alkyne. So any one of these will work. So I said that NH2 minus will work, so that's sodium amide. And then the conjugate base of butane will work, and where we get that is from butyllithium. So we call this butyllithium, so that's a strong enough base. And of course, the hydride ion, we get that from sodium hydride. So again, our list, did I put NH3 instead of NH2? Oh, Mr. Dion. Okay, so what are the bases we can use? Bases that are strong enough are going to be sodium amide, butyllithium, and sodium hydride. Those are the three. Now, again, the textbook uses this one the most, but any one of these will work. And you see that none of the alkoxides are strong enough, right? T-butoxide, ethoxide, hydroxide, none of those will suffice. Why? Because the pKa of their conjugate acid is lower than the terminal alkyne. And so if you have a lower pKa, that means it's a stronger acid, so that means it produces a weaker base. All right? So that's kind of the rationale there. And so it says here, in each of the following cases, determine if the base is sufficiently strong to deprotonate the terminal alkyne. Well, obviously the first case is correct because I told you 1,000 times that sodium amide would totally work. So let's see here. If we just draw the products, and you could even practice the mechanism by drawing the amide ion and saying, well, that's just going to do a proton transfer like this. So we end up with NH3, ammonia, plus our, maybe that's not my best artwork, let me see here, plus our acetylide, so it's going to look, our alkanide, which is going to look like this. There we go, that's a little bit better. So the pKa of the proton of the terminal alkyne is 25, and the pKa of ammonia is 36. So 35, 36, we'll just put 36. So that means that the equilibrium is going to lie to the side of the products, and so the answer is yes. Sodium amide is great. Now, I already told you that sodium hydride is going to work. You could practice your mechanism again here, our proton transfer. So we're going to rip off this proton and make the alkanide. So this is obviously going to work as well. So we end up with hydrogen gas once the hydride takes a proton plus the alkanide, which looks like this. Okay, and if we compare the relative pKa's, again, the pKa here is equal to 25, and the pKa of hydrogen gas is around 35. So pKa is equal to 35. So yes, hydride is going to be just fine and dandy like sour candy. But if we look at butoxide, well, you probably already know that this isn't going to work, right? It might deprotonate a little bit, but it's mostly going to lie to this side. So we'll put a big no over this already. And again, the reason why is if some of the T-butoxide ions did do a deprotonation, then we could even draw the curved arrows because it will deprotonate maybe a little bit, but you would end up with your terbutanol, which is an alcohol, plus you end up with your alkanide, which is going to be this compound here. So if we compare the pKa's, we'll put here in purple maybe for a change. We have a pKa that's equal to 25 here, but the pKa of an alcohol is going to be in the teens, right? The pKa of terbutanol is somewhere around 15. And so the equilibrium is going to lie towards the sides of the reactants. The weaker acid, of course, is going to be the acetylene derivative or the alkyne. All right, give me a thumbs up if you're with me on that. Like, yeah, that's not too bad. Okay, deprotonation, strong bases that we want to use. And again, the strong bases that we're going to see in this book are going to be sodium amide, okay, butyllithium, it's also going to work, and sodium hydride, right? Those are the bases that are strong enough. All right, so let's talk about how you make an alkyne. So how would you make an alkyne? The good news is that you kind of use reactions from chapter 7 and 8. So again, there's nothing really majorly new here. It says, like an alkene, an alkyne can also be prepared by an elimination reaction. So this is kind of like via an E2 reaction. Now, in order to make an alkyne, we need a dihalide. Okay, so I want you to keep that in mind. You've got to have a dihalide in order to make an alkyne. If you just have a regular old halide, like this one here, this is one halogen, then you can use a strong base to make an alkene. So let's say you have a base here. I'll just write some generic base like this. What's it going to do is it's going to do an E2 reaction. You're going to abstract your proton, form your double bond, and lose your leaving group. There's nothing really new here. But if you have a dihalide, you have to do a double elimination. You have to eliminate twice in order to make an alkyne. So what's the mechanism going to look like? Well, it's going to look like this here. You're going to do one E2 reaction, okay, the first E2, and then once you do that, you make an alkene, and then you have to do a second E2 reaction to make your alkyne. The only time this works is if you have a geminal dihalide. Okay, so remember Gemini, so this is like twins, right? So twins, so that means the two halogens are going to be on the same carbon, like we have here, geminal or vicinal, okay, or vicinal dihalides. Now, the only thing that we're going to see in this class is how to make a vicinal dihalide. We never talked about how to make a geminal dihalide, I think. So really, the only thing we'll see is vicinal. But it's the exact same mechanism, okay? You just do one E2 and a second E2, and you form your alkyne like that. So what would you do? If you have a dihalide, this one is geminal, right? This one here, you do excess sodium amide, or you can put two equivalents, but generally we just put excess sodium amide, and that takes us all the way from here to the terminal alkyne. Now, you know that this proton has a pKa equal to 25. So you know that if you're using excess sodium amide, it's going to deprotonate that to take you all the way to the alkylide. So what do you have to do? You're going to have to put water in the reaction mixture after in order to protonate, or to put a proton on the end of the alkylide to restore neutrality to it, to the molecule. So overall, this is what the process looks like. Okay, you do excess sodium amide in ammonia, and ammonia is your solvent. Okay, and then you treat it with water at the end. And the reason why you have to treat it with water is because after the first step, what you end up with is this. You end up with the alkynide, okay? But then in the second step, you treat it with water, and you do a proton transfer in the second step, just like this. So I'll use my green pen like that. Okay, so it's a two-step process. Two-step process. First step, excess sodium amide in ammonia. Second step is water. Now, again, this is a geminal dihalide. Geminal. But the same thing would work if it was vicinal. So if you took 1, 2, 3, 4, 5 carbons, and if you had a vicinal dihalide, like this, okay, you could do the exact same thing. So this is vicinal. Okay. Step 1, excess sodium amide in ammonia. Step 2, water. It's going to give you the exact same product. Okay, it doesn't matter if it's vicinal or geminal, you're going to get the exact same product. All right, so with that in mind, let's try a practice problem. It's question 9.7. It says for each of the following transformations, predict the major product and draw a mechanism. So this is a geminal dihalide, right? Both halogens are on the same carbon, and this one is vicinal. You have two halogens on adjacent carbons, right? These carbons, carbon in red and carbon in blue, they're next door to each other. So let's start with the first one, and maybe we'll save the second one for another day. So we've got our amide ion. That's going to remove a proton. So where is it going to remove a proton? Well, there's only one place where there's beta protons here. So let me just erase this, okay? And that's going to be these protons here. So I'll put one in red and I'll put one in blue. It doesn't matter if they're color-coded or not, but anyhow, so we're going to abstract one of the protons, make a double bond, and lose a bromine. So what's that going to look like? That's going to give us this intermediate, where we're going to have a double bond here, and we've got a bromine here. So remember, and there's also a proton in black, so we'll put this one in black. So now you've got the one in blue, and you've got the proton in black. You've got these two guys left. So remember, you've got excess sodium amide. So you've got lots of sodium amide. So now a second molecule of the amide ion is going to remove the second proton. You form the triple bond and you lose the leading group. So now you've got your alkyne like this, and you've got the proton in black, and you think, well, that's done. That's the end. That's the product. No, not so fast, because you've got excess sodium amide, and that proton is very acidic in front of that amide. And so that's going to deprotonate it to give you the alkanide. So let's draw the alkanide, which is going to look like this. Right? It's going to look like that. So then to get to the product, you have to put water in the last step. So we've got H2O in the last step, and that is going to do a proton transfer like this, and that's going to give you the product. So we end up with our terminal alkyne, and I'll circle this proton in green. So the proton that's on the end, when you get the final product, that came from the water molecule. All right. So I want you to give this one a try. So try this, and we might come back to this on another lecture.